Hereditary properties and Leizhen theorem. Definition 3.14 Hereditary property. If pi is a property of graphs, we say a graph G is a pi graph if and only if G satisfies pi. We say that a property pi is a hereditary property if given any pi graph G, whenever H is an induced subgraph of G, then H is a pi graph. The literature is filled with many graph modification problems. As Leizhen remarks, in general, these problems can be placed in the categories below. 1. The age deletion problems find a set of ages of minima cardinality whose removal results in a pi graph. 2. The vertex delete problem find a set of vertices of minima cardinality whose removal results in a pi graph. 3. The H vertex deletion problems. Categories 1 and 2 combined. 4. The H addition problem find a set of new ages of minima cardinality whose addition results in a pi graph. It is known that categories 1, 2, and 3 are usually empty-hard for any non-trivial hereditary property. Leizhen considered the following general parametric version of the modification problem. Pi ijk, graph modification problem. Input, a graph G equals to VE. Parameters, non-negative integers I, J, and K. Question, can we delete at most I vertices, J ages, and add at most K ages and get a pi graph? We will say that a property pi has a forbidden set characterization. If and only if there exists a set F of graphs such that G is a pi graph if and only if G does not contain a member of F as an induced subgraph. If we can take F to be finite, then we say that pi has a finite forbidden set characterization. Clearly, if F is a finite set characterizing pi, then there is a p-time recognition algorithm for the pi ijk graph modification problem for any fixed I, J, and K as follows. Let n be the maximum number of vertices of any graph in F. Given a graph Q, we can check whether Q is a pi graph in time big O of the size of Q to the n by checking if Q prime has an induced subgraph with less than equals to n vertices in F. Therefore, the pi ijk graph modification problem is solvable in time big O of the size of G to I plus 2J plus 2K plus N. However, used essentially the problem kernel method to prove the result below. Theorem 3.15 Leizhen suppose that pi is any property with a finite forbidden set characterization. Then the pi ijk graph modification problem is FBT in time big O of n to the I plus 2j plus 2k times the size of G to the n plus 1, where n denotes the maximum size of the vertex set of any graph in the forbidden set F. We need the lemma below. Lemma 3.16 Leizhen for any hereditary property pi, if pi is recognizable in time t of G for any graph G, then for any graph G which is not a pi graph, a minimum forbidden induced subgraph for pi can be found in time big O of the size of V of G times T of G. Prove that A be the recognition algorithm for pi running in time T of G, so that A of G equals to 1 if and only if G is a pi graph. So first use A of G to see if G is a pi graph. Assuming that the answer is no, we perform the following algorithm. Order the vertices of G as V0, V1, V2 until Vn, the set of that, the algorithm proceeds in stages. At stage 0, G0 equals to G. At stage S, using A applied to Gs minus the set of only one vertex Vs, see if Gs minus the set of Vs is a pi graph. If the answer is yes, then V must belong to a minimal forbidden induced subgraph, and we let Gs plus 1 equals to Gs. If the answer is no, then we define Gs plus 1 equals to Gs minus the set of Vs. In this case, Gs minus the set of Vs must contain a minimal forbidden induced subgraph. Clearly, if G is not a pi graph, then Gn plus 1 is a minimal induced forbidden subgraph, as required. Proof of Theorem 3.15. Fix I, J, and K. Assuming that G is not a pi graph, we will repeat the following steps until we either get a pi graph or we have used up the deletion of less than equals to I vertices, less than equals to J edges, and the addition of less than equals to K edges. In this later case, we output no. Step 1. Find a minimal forbidden induced subgraph H of G. Step 2. Modify G either by deleting an edge or a vertex or adding an edge to H. The crucial idea is to modify only minimal induced forbidden subgraphs. It is clear that the algorithm works. Now, using the finite set characterization, we can recognize if G is a pi graph in time big O of the size of V of G to the n. Therefore, by lemma 3.16, we can compute a minimal induced forbidden subgraph H of G in time big O of size of V of G to the n plus 1, since n is the largest number of vertices of any member of the forbidden set F. There are at most and just too many ways to add or delete an edge of H, and at most and many ways to delete a vertex from H. The total number of graphs we can generate in the algorithm above is thus n to the I times n choose to the j plus k, which is big O of n to the I plus 2j plus 2k. The running time of the algorithm is thus big O of n to the I plus 2j plus 2k times the size of V of G to the n plus 1, as required. The reader should note that there are several interesting pi ijk graph modification problems that are not characterized by a finite forbidden set and yet are still FPT. One important example is minimum fill-in, also called chorograph completion, which asks if we can add k edges to G to make a chorograph. A chorograph where any cycle of length greater than 3 contains a chord. This problem is very important in the area of computational biology called perfect phylogeny. Chorograph completion is a pi 00k graph modification problem which is classically NP-hard. Please see the paper of Professor Yanakakis. There is no finite forbidden set characterization. Nevertheless, chorograph completion is FPT. Chorograph completion provides an interesting example of an FPT problem since there are several algorithms to demonstrate this fact. Kaplan, Shamir, and Tarjan used the method of bounded search trees to show that the parameterized version above is strongly uniformly FPT in time big O of 2 to the 4k times the size of E of G. Kaplan, Shamir, and Tarjan also used essentially the problem kernel method to give a big O of k to the 5th times the size of V of G times the size of E of G plus f of k for suitably chosen recursive f. Finally, Leizhen Kai also used the problem kernel method to give a big O of 40 times k plus 1 to the minus 3/2 times the size of E of g times the size of V of g plus the size of V of g to the square time algorithm. There are a number of interesting related problems which are not known to be FPT. They include interval graph completion, chordal graph deletion, bipartite graph deletion, and interval graph deletion. In each case, the parameter is a positive integer k, and the problem is to add or delete as the case may be k addresses to make the graph have the relevant property.